Hello, ladies and gentlemen, and welcome to the Amazon Web Services Partner Webinar Series. Our topic today is Best Practices for Running Apache Cassandra on AWS. I'm your host, Maya Kabasi, with the Partner Marketing team here in Seattle. I'd like to start with a couple of housekeeping items. We are recording today's webinar, and while lines are muted, you can submit questions anytime during the presentation. Use the Q&A widget in your browser to do so. We'll take time for questions at the end. In addition, this presentation will be available for on-demand. You may find our webinar recording and materials available on AWS YouTube channels. Let's welcome our presenters. Joey Imbaciana, Automation Engineer at Stackdriver, and Miles Ward, Senior Solutions Architect with Amazon Web Services. One of our presenters, Matt Stump from DataStax, could not join us today due to unforeseen circumstances. We apologize for the last-minute change in plans, but we'll have plenty of interesting content. On the agenda, we'll begin with Miles Ward, who will provide an overview of Amazon Web Services and NoSQL, and pass the mic to Joey, who will talk about running Cassandra on AWS. We'll wrap up with a Q&A. So without further delay, let me turn it over to Miles, Senior Solutions Architect with Amazon Web Services. Take it away, Miles.
Maya, thanks a bunch. Everyone, I really appreciate you taking the time this morning to join us in diving into how NoSQL works, what are the options for NoSQL systems on AWS, and I think a really powerful set of hands-on technical content from our friends at Stackdriver and DataStax around one of the most popular NoSQL options on AWS, Cassandra. So we've heard from lots of customers as we've been growing over the last 8 years that cloud as an infrastructure choice, as a system for deploying all kinds of different workloads, from web applications to enterprise applications to data systems to databases to NoSQL databases, that all of those different tools, they capture a really clear, specific set of business benefits that differentiates cloud from other approaches to building these kinds of tools. We hear from customers all the time that they want to build systems without an upfront capital investment. They want to move dollars from their CapEx budgets into operational budgets. And those dollars, they want them to be as small as possible. They like to run systems as inexpensively as they can. They also want to only pay for what they actually use. Lots of different tools are out there for, your second copy and your third copy and your fourth copy of data, or the backup to the backup to the backup of your infrastructure. If you don't use that stuff, you shouldn't pay for it. We've also seen that no provider, doesn't matter who they are, is fast enough to keep up with the genius of its customers. And so we want to make sure that each of these systems is self-service. We've had a lot of customers that have found huge value from, frankly, us getting out of the way and letting them build whatever they want, whenever they want on top of our infrastructure. And because of that control, we've made it so that you can scale up and down to meet your actual customer or project demands in a way that's so much more nimble than buying and ordering physical devices. So that set of benefits stands to provide a whole series of actual resources. So AWS has built this giant global infrastructure. We'll show how that's distributed here in a second. That global infrastructure supports many, many, many data centers. Inside of those data centers, we have enterprise-grade, high-tier networking that allows people to implement high-performance web applications, enterprise applications, business intelligence suites, data processing fabrics, all manner of interesting stuff. And that infrastructure, those hypervisor and virtualization tools that we've provided to allow people to create resources on demand, generate 3 basic building blocks: the access to compute as a service, that's called Elastic Compute Cloud, or EC2, several different storage services from EC2 instances that are optimized for storage, to S3, one of the largest data storage systems in the world, where over 2 trillion objects stored there to date, into our own NoSQL data storage services like SimpleDB and DynamoDB. We also have relational database services that manage kind of old school database types. And then above those resources, we've built even more application services and tools for deployment and administration that make it easier to consume resources. That set of tools, we think, and we continue to improve and iterate on that set of tools, but we think it makes it easier to build high-performance, productive infrastructures than anywhere else in the world. And speaking of around the world, you can do that in 9 different regions today, across the planet, 4 different continents. Each of those regions is subdivided into distinct availability zones, which you can think of as one or many data center buildings. What that allows you to do is to develop for high availability, where you have more than one instance or virtual machine or service running a given workload, so that if one side of a region were to have a problem, the other side could take over. Or if a single virtual machine were to fail, you'd be able to take over. That's a part of an Amazonian general principle of designing for failure that AWS has built into powering some of the biggest and most successful online businesses in the world. And not just web-based content, but we've also done work for, in myriad sectors across oil and gas, space exploration, video processing, anything that you can do with a computer that you don't have to lay your hands on. AWS has some customer somewhere doing that great stuff. And in each of these businesses, we're not talking typically about little experimentation, although AWS is a great place for those kinds of work. You only have to run infrastructure as long as you need it. So if you want to do a test for 2 hours, you pay us for 2 hours. It doesn't matter to us. But these businesses on the side, and frankly thousands and thousands of others, are running real production, top tier, in front of customers, betting the farm on AWS. And they're not alone. We've worked with lots of different businesses. Gartner just made this analysis that shows a pretty clear gap between running infrastructure and running at scale on AWS and really any other way of doing this stuff. Their quote, not ours, is that AWS in production has 5 times as much running infrastructure as all the other 14 participants on this chart combined. So we're a significant player in this market space. We're excited to see the brand new, exciting applications that our customers are able to deploy on top of this infrastructure every day. And there is a huge variety of those applications. What we're talking about today, and the place we're going to focus on, is really looking in at database services on AWS. How do NoSQL databases work? And there's probably a little value we can put in to help you understand the differences between these different options, because there really are a huge number of them. So, starting maybe with the most traditional application, relational database management systems, or RDBMS systems. AWS runs those on EC2, which is our Elastic Compute Cloud, on demand, available to you. So if you want to run an Oracle relational database, you can boot those on demand. You want to run SQL Server from Microsoft, you can boot those on demand. You want to run MySQL databases, or frankly any one of a myriad others, Postgres, DB2, Informix. There are dozens in this category. And those applications and that application style is something that's been very consistent for a long time. It embodies a concept called ACID transactionality, which means that those databases record and confirm recording of each individual transactional event before returning any reads against that event. It confirms what's called consistency. And that consistency is a part of 3 different sides of a theory of data management called the CAP theorem. The CAP theorem demands that for any data system, consistency and availability and network partition tolerance, or P partition tolerance, are 3 values that you might want in a given database system, but that any basic system available will only be able to deliver 2 of those. So for most relational databases, they've chosen consistency, clearly need the C part of that, and they've chosen availability of data at the expense of partition tolerance. What that means is that it's typically really complicated to do what's called scaling out, or using more than one computer to power a database. For most database applications, you use bigger and bigger and more powerful computers in order to be able to deliver consistent, high-performance transactions. And as you and I know, it can be complicated. Eventually, these big database systems are clearly going to be asked to do things that a single computer cannot do, no matter how big they are. Today, AWS supports what's called a CR1 8x large. That's 10 gigabit networking, 32 VP eCPUs, and 244 gigs of RAM with solid-state storage. That's very high performance, allows very big databases. But there are workloads running on AWS that would take dozens and dozens of those computers to accommodate. So how do you build a system that can manage even bigger than these relational databases? Well, in many tools, you also are looking at a way to get more efficiency out of a given set of compute resources. Because you can imagine there are also workloads where that hard transactional rule isn't a firm requirement. Maybe, I think an easy example lots of people can identify with would be American Idol. They're in the middle of counting the number of votes for someone who, to figure out which of the three contestants is going to be the one who wins. And everyone wants to vote all at the same time. This system maybe is only used for 60 seconds. So that kind of a workload, you can imagine, you want to be able to show an update really quickly of the current number of votes, and you have potentially millions of simultaneous voters interacting with a tool like that. So that kind of workload, it's not crucial that you're exactly right in the middle of the voting. Right? If you're off by one or two, that's probably okay. It's more important to show the general upward trend to be able to capture that data. Another example would be, like leaderboards or scoreboards. And there's lots of other data systems where this kind of non-consistency, or eventual consistency as it's called, can be really valuable. It turns out that in software tools, if you're able to support eventual consistency and relax the requirements of ACID transactionality, you can actually get to incredibly higher performance, particularly higher performance per unit of compute. And it also allows you to change which of those 2 out of 3 of the CAP theorem that you choose. So if relational databases choose consistency and availability, you can choose availability and partition tolerance, A and P, and now you have the ability to run distributed, horizontally scaled fleets of infrastructure that can deliver very, very high performance systems for data management at much lower cost, at much higher availability. So NoSQL databases also support a variety of different APIs or services that they expose. Maybe the most complicated of those, or the richest of the APIs, sit in the document store category, where you have the ability to do some kinds of indexing and the ability to do secondary indexes and global indexes to query on values, maybe a little bit more like a relational database would allow, geo lookups and other tools. You also have a relationship between the NoSQL data store development movement and new classes of software development, where if you look at object-oriented programming, it can be really useful to have a database that is itself object-oriented. So that key value binding pair, where you say, for this key, I want to store this value, as the simplest kind of data model, is embodied by lots of different software applications that are trying to capitalize on the higher efficiency associated with being able to choose availability and partition tolerance out of the CAP theorem. So today there are myriad NoSQL databases running on EC2 that you can install and manage on your own. We also have our own managed NoSQL database services in SimpleDB and DynamoDB. And you can think of our storage service, S3, as a key value storage service optimized for very large values. It's also very, very large and was built in the context of the general work around the Dynamo technology, which is a white paper that Amazon produced, which allows and provided for a lot of this kind of research. There are also other kinds of data storage systems. It's not only the differences between relational and NoSQL. There are also tools for data warehousing, tools for MapReduce analysis, and lots of other systems. But today, what we're going to focus in on is one of the options. And I think that there's a lot of really successful customers that have focused on running Cassandra on AWS. And Cassandra is very, very popular, one of the most popular NoSQL databases that's running on AWS today. And one of our partners, Stackdriver, has a lot of really useful hands-on experience with Cassandra that they'd love to share. I think what that'll do is help you come away with better tools for deploying and designing your own NoSQL data system on AWS. With that, I'd love to hand it over to Joey because I'm excited to hear what he's got to say about Cassandra.
All right. Hi, everyone. I'm Joey Ambassiano. I'm a cloud platform engineer here at Stackdriver, and I just wanted to thank you for joining us on this webinar this morning. So I just want to give you a little bit of background about me. I've been working with AWS as a platform for about 3 years now, doing hosting and SaaS services. And my focus is really in operations and automation on top of AWS. So today with Cassandra, I'm going to be talking about the problem that we're trying to solve at Stackdriver with Cassandra. And by doing that, I'm going to give you a brief intro into the architecture here, tell you why we chose Cassandra and some of the alternatives that we considered, go into a little bit of a deep dive on our Cassandra configuration, including AWS-specific configuration, go over briefly some automation and tooling that we've done, and then tell you a little bit about how we've changed how we do disaster recovery and backups by utilizing S3 and Cassandra. So to start out, the problem that we're trying to solve is that Stackdriver provides customer cloud-hosted applications with monitoring and inventory data. And so what we're doing is we're collecting from cloud providers an inventory of each of our customer systems. So that includes things like EC2 nodes, ELBs, SQS, Elasticache. We're also collecting information about services that are running on top of EC2. So these include services like Mongo, Cassandra, Nginx, Redis, and Elasticsearch. And what we're doing is we're collecting metrics for each of these services. So as you can see here in this screenshot, this is an ELB dashboard that on the left you can see the inventory, and on the right you can see performance data for latency and the number of requests per second that these ELBs are getting. So our data, we're collecting all of this data about each of these inventory items and services, and our data is primarily a time series data. So for each one of these points, there is a timestamp and a value. And each one of these lines is keyed by the metric that we're collecting. So this data model fits, as you'll see, really well into how Cassandra works. So some of the things that we're trying to do with this data is we allow you to group your resources into how you think about your infrastructure. So in being able to dynamically group these resources, we have to have a lot of data online in order to perform things like aggregations and allow you to create graphs kind of on the fly of performance metrics that are aggregated across clusters of resources. So obviously we can't predict what kind of dashboard that you want to build ahead of time. So we need all of this data online and ready to go so we can present you with the best possible dashboard to solve a problem. And then one other thing that we're doing for customers is we're doing analysis on the data. So we're generating things like weekly reports to tell you give you recommendations about capacity and any potential issues that you'll have in your infrastructure. So again, we need all of this data online in order to do these reports, and this is where Cassandra comes into play. So just to give you a brief overview of the architecture and how Cassandra fits in. So as you can see, the diagram on the right, the data is flowing from bottom to top. So we have two different layers of two different pipelines that are feeding into Cassandra. The first pipeline is an analysis pipeline, and this is data that's coming in batch. So we'll do things like compute aggregations, create recommendations, and save this data into Cassandra. And another pipeline that's coming in is an indexing pipeline. So this is all the sensor data is coming into our service, and we're immediately saving it into Cassandra. And what this allows us to do is it allows us to show you, as soon as the data comes in, the data on each one of your dashboards. So you don't have to wait for any of the slow analysis or batch jobs to insert other data. So then there's also a query layer that sits on top of Cassandra, and this is basically an API that we've designed that allows us to ask questions and give answers. So the simplest question is give me the performance data for this ELB between midnight and 12 p.m. And then we can ask other questions like give me the aggregated data for a group of resources between such and such a time. And then another path that we actually won't get into on this webinar is an alerting pipeline. But that's not discussed here. So why did we choose Cassandra? I think this is something that's really important and that always kind of comes up in conversations. So Cassandra has a true peer-to-peer architecture. So there are no special nodes, there are no masters, there are no slaves. And what this allows us to do is it allows us to add and remove capacity, and we don't care which node we're removing. We don't care what kind of node we're adding. It really simplifies the operational aspect of running the database. Cassandra has great support for write-heavy workloads. The majority of our data coming in is writes. So, there's an order of magnitude more data that we're writing to Cassandra than we're reading out. So the data model, Cassandra basically is an append-only storage. So the time series data that's coming in for each one of these services is really compatible with Cassandra. Your row key is the metric that's coming in, and then each value is a timestamp and the value of the measurement that we've taken. And Cassandra allows you to just keep appending to this row, and it works really well. And then Cassandra is built, from the ground up as a distributed database. So it allows us to achieve high availability really easily in AWS by distributing across availability zones. So you'll see in a couple slides, how we do this. So just to go over a couple other options that we considered when approaching this problem. MySQL, a lot of us on the Stackdriver team had experience with operating large sharded deployments of MySQL, and operationally it was really complex, very error prone, very manual, and it was a challenge that we didn't feel like we could win. And the relational data model, we're adding all new kinds of metrics every day, and to have to define that schema ahead of time and do the kind of schema updates that we would have to do, it just wouldn't work. HBase, was another contender. Again, operational complexity that we really we didn't want to deal with. It requires Zookeeper, HDFS, and it has a special master role. And again, like when you're working in AWS, special nodes, it doesn't work out well. Just to give you a little bit more insight on the architecture before we dive into the Cassandra specifics. So on the left in this diagram is the indexing path that I was talking about earlier, and data coming into our service goes directly into Cassandra through this indexing path. The archival path, which is really important when we're talking about disaster recovery and recovery in general, is really important to us. So data coming into our service also goes down an archival path. So immediately we'll put the data not only into Cassandra but also into S3. And then we'll also replicate this data to multiple regions with S3. And what this allows us to do is have, as you'll see later on, is have a path to disaster recovery if a region was ever out in AWS. And one of the important things in the Stackdriver architecture is that the majority of the pieces are stateless, and in order to scale our service as customers grow and as we acquire new customers, is that we horizontally scale each one of the stateless services. So we needed a database that could also scale horizontally just like our other services that we've built. So Cassandra does this really easily, and we'll get into this. And just one other key area that comes into play in the Stackdriver architecture is Cassandra. We treat that as a soft state. So you'll see that we don't, the way we do backup and recovery is not dependent on Cassandra. And I think that makes us, our use of Cassandra in AWS really unique. So here we get into details about our Cassandra configuration here at Stackdriver. So we're using the DataStax Community Edition. You can see the version here. And what DataStax gives us is a packaged version of the open source Apache Cassandra, and comes with really helpful run scripts. It comes with additional tunings that they've recommended, and it's all bundled in an RPM. So we run our Cassandra with a replication factor of 3. And what this means is that for every write that we do to Cassandra, the write is replicated to a total of 3 nodes. So in the case of an outage of an availability zone, we'll still have the data in 2 other availability zones. And what this allows us to do is still achieve a quorum when we do reads or writes, even in the case of an outage. One thing that Cassandra introduced in version 1.2 is the vnodes and Murmur 3 partitioning. So in version 1.2, vnodes, they take care of how the data is distributed over the nodes when you add and remove nodes. In previous versions of Cassandra, you had to manage these token ring positions, and the tokens described where data went. And when you're constantly adding and removing nodes, you had to pre-calculate basically where the position was that you wanted your data to go. And I found it to be pretty error-prone if you didn't really plan ahead. But Cassandra, took this as a serious problem and really made it a lot simpler in version 1.2. So what vnodes do is when you add and remove servers from your Cassandra ring, it redistributes the data automatically. So it takes care of all of the ring partitioning that you had to do in the past. And what the Murmur 3 partitioner does is it tells the data where to go. So it is like a random partitioner that ensures that your data is evenly distributed throughout your ring. So specific to AWS, one of the plugins that you can use with Apache Cassandra is an EC2 snitch. And what the EC2 snitch allows you to do is, first of all, it aids in request efficiency. So when you make a request to Cassandra, requests are routed in an availability zone. So you actually get a lower latency. And what the EC2 snitch is really doing is it's allowing Cassandra to be Amazon aware. So it knows about where the node is in relation to other nodes. So if you have nodes in US East 1A, B, and C, each of the Cassandra nodes actually knows where the other ones are. And the other thing that the EC2 snitch gives you is that it enables Cassandra to ensure replicas are in different availability zones. And this is, probably the most important thing. So since each of the Cassandra nodes knows where it is and where other nodes are, when it goes to replicate data, it can ensure that when you have a replication factor of 3, that data is actually living in 3 different availability zones. And obviously this is important because if an availability zone were to go out, you wouldn't want all 3 replicas to be in the same data center. And then one other setting that I feel is a little bit hidden, but I think is worth mentioning is this phi convict threshold. And this is used to determine when nodes are down. And this is actually a DataStax recommendation. So the AWS network can be a little noisy. And by increasing the threshold from 8 to 12, you'll find that nodes will give each other a little bit more time to respond before being marked as down. And this just helps, I found, in operations on top of AWS. So here's a visual of our Cassandra topology in AWS. And on the left is where we started. We started, last July as a company, and so we had a little 3-node cluster running in A, B, and C in US East. And as we've grown and our customers have grown, we've had to scale this out. We've scaled our entire infrastructure out, but Cassandra's been a key piece, obviously. So we actually started with 1, 2, and 3, and we're up to 36-node cluster in AWS, distributed evenly across each of the availability zones. So as you can see on the right, it's grown quite a bit. And from an operational perspective, it's been really fun to work with. So we'll double our traffic in a day, and we'll double the size of the Cassandra cluster. We'll go up 50% the next week. We'll go up 50% on the Cassandra cluster. It's really painless and really fun to work with. So this gives you a visual of kind of growing this out and across each of the availability zones. So here's some specific Cassandra EC2 node configuration. So here at Stackdriver, we use an M1XL, and an M1XL has 4 cores at 2 ECUs each. They have 15 gigabytes of RAM and 4 ephemeral disks available. And actually, the most important thing to us is the 4 ephemeral disks, and I'll explain why in a bit. But I've also found that it's for our specific write workload, this combination of 4 cores and 15 gigabytes of RAM has really served us well. The reason the 4 ephemeral disks are really important is that so when Cassandra writes data, it writes it first to the commit log. The commit log is a sequential write on the disk. And then when there's enough data to compact, it compacts them into these data tables. And the compaction is really expensive on the disk. So again, this is actually a DataStax recommendation, but I think it's pretty important to point out. So you not only have the sequential writes going to this 4-disk RAID 0, but you also have this compaction that's going on, which is reading and writing data non-sequentially on these disks. So the RAID 0 of these 4 disks gives you the most I/O that you can get on ephemeral disks. Just a couple other settings that we've found and benchmarked. ext4 with default and no wait time has given us great results as far as the file system. We use MDADM for RAID 0. And again, there's just these disks just have really heavy read-write I/O to them. So again, this is why we use RAID 0. If one of the disks fails, we actually fail the entire node, and we'll replace it in the Cassandra cluster. So we're not worried about high availability on the disks, because Cassandra's taking care of this for us at the application layer. So I'm just going to touch on some of the automation and operational things that we do in our platform. And this isn't Cassandra specific, but Cassandra does fall under our tool set here for automation. So we use a combination of Bodo, Fabric, and Puppet. And for those of you who aren't familiar, Bodo is the Python library for interacting with the AWS API. So this allows us to create instances, destroy instances, and anything that you need to do against the Amazon API. Fabric is an orchestration library for Python. It allows you to SSH in to one or multiple nodes, execute commands, get results, things like that. Puppet is a configuration management tool, and what that allows you to do is, in a declarative language, define what the state of a node should look like. So using a combination of these tools, we can provision a new node, put Puppet code onto it, and then execute Puppet to turn a node into a Cassandra server. And by bootstrapping it into the Cassandra ring, we have one command to launch a new cluster, a new node. We can replace dead nodes, replace existing nodes, and do the growing and shrinking basically in one command. So we have an internal slogan and a great poster here at Stackdriver. And what could possibly go wrong? So you always have to be thinking about failure. And so we've taken, I think, a unique approach into thinking about failure when it comes to Cassandra. So we don't use Cassandra-powered backups. One of the luxuries of working on Amazon is you have S3, and we've had a great experience with S3. So what we do is all the data that comes into our SaaS service, I mentioned this earlier, but I'll mention it again, is written immediately to S3. And what this allows us to do is we've written tools that will read this data out of S3 and replay it back into our Cassandra cluster. So in the event of a catastrophic failure of our Cassandra cluster, or a severe outage, or maybe there's a bug that affected data, we have the ability to load data from S3 into our tool called the bulk loader. We use tools like Elastic MapReduce to run all the data and aggregations and computations that we've run before on the data, and all of this gets pumped back into Cassandra. And we can do this on demand, and it's allowed us to do things like take a major version upgrade of Cassandra without being worried. So what we'll do is we'll have our existing Cassandra cluster running. We'll bring up a new major version alongside of it. We'll replay all of the data that was played into the original cluster into the one alongside of it. And then we have tools for cutting over part of our traffic to the new Cassandra cluster to make sure that everything's great. When everything's stamped and ready to go, we'll cut over the rest of our infrastructure, and then we'll be running on the new Cassandra cluster. And when everything is all set and ready to go, we'll spin down the old Cassandra cluster and we'll throw it away. And this has allowed us to be really confident in taking on new database upgrades, making changes, and really staying agile as an engineering organization. So just to show you, this is a bulk load in action. So as you can see, this happened back in April, but on Tuesday we started a bulk load. The load on our Cassandra cluster got pretty high, and then once everything caught up by Saturday, it was back to normal, and that was a successful bulk load of a new Cassandra cluster. So that's the end of my talk. I'm going to hand the mic over to Maya, who's going to lead the Q&A.
Thank you all for demonstrating the best practices for running Apache Cassandra on AWS. And yeah, let's open it for a Q&A. I already see a few questions from the audience. I'm going to start with a question that I will direct it to you, Joey. Geographically dispersed nodes, don't they cause any anomalies?
So I want to make sure I understand the questions. So I think you're talking about if the nodes are geographically dispersed, won't the data be inconsistent? Consistency is, I think, always a concern when we start to talk about these NoSQL databases. But what Cassandra allows you to do is it allows you to tune your consistency. So remember I was talking about our configuration where we have a replication factor of 3. So that means up to 3 nodes can receive a total of 3 nodes receive a copy of the data. So what you can do is if your application requires high consistency, you can write at local quorum or all. And what this means is that if you write at local quorum, then 2 nodes have to confirm that they've received, 2 out of 3 nodes have to confirm that they've received the write. If you write at a consistency level of all, that means all the nodes have to confirm, that they received the write, and that prevents any inconsistencies that you might find. Cassandra comes with tools for also finding and repairing any inconsistencies that might have occurred, and these are called repairs. So if you're interested in something and going in deeper on this, you can look at the Cassandra documentation around repairing and inconsistencies.
Thank you. Let's move on to the next question. What type of compaction strategy do you use on your tables? Do you stay with the default, or do you tweak it per table?
Good question. So we use size-tiered compaction, and we've done very light tweaking, only around the throughput for compaction, and right now we haven't had to tune any of additional compaction options. There are a ton of knobs that you can tune around compaction. We just haven't had the need yet.
Well, as a follow-up question, how many nodes do you add at a time when scaling out your cluster? Do you stagger the node additions or do it all at once? How long does it take?
Yeah, so it kind of depends. So it depends how much capacity I'm adding. If I need to add a lot of capacity, we will serially bootstrap nodes into the cluster. But once a node starts to join, after 2 minutes, we'll bootstrap the next one. So the way it works is that we'll bootstrap a node. It'll go into joining. Once it's in joining for 2 minutes, we'll start the next one. So I think the most that I've done at a time is either 5 or 6.
Thank you, Joey. One more question for you, and then I would like to switch gears and ask a few questions to Miles from AWS. Is your cluster size driven by read-write load or by storage requirements?
Yeah, another great question. So primarily it's driven by write load, but we actually have a little bit of a mixed workload since we are doing some read-heavy operations. And so primarily by write load, and then secondarily by the read load. Storage requirements, not so much, because by the time we've added enough capacity to handle our write load, the storage is distributed enough.
Thank you, Joey. Miles, does Cassandra work on AWS's HI 1.4x large instances with local SSD? What about CR 1.8x large?
Sure, Maya. So the implementation that the folks from Stackdriver have designed is outstanding, and it's built on the concept of using several different nodes to be able to distribute the Cassandra workload. And M1 extra large instances are available in every AWS region. So you could even duplicate this system 9 different times on 4 different continents. In the United States and EU, a couple of our facilities, we have systems that are even higher performance. So we heard from customers as they went from 3 to 6 to 9 to 90 to 180 to 360 M1 extra large instances running their Cassandra fleet, that they needed higher performance density. And in particular for some workloads where storage density was more important than getting more compute power or more memory. So we've built instances that use solid-state disks rather than standard rotational media like are in the M1 extra large instances. And those solid-state drives give you 2 terabytes of local storage, add up to 85,000 read operations per second on that storage. So for Cassandra workloads, particularly ones that are storage performance sensitive, those instances are much bigger, much higher density, and can be more efficient at delivering the same workload if you're at a scale where that big makes sense. We also have some customers that have, say, a slightly somewhat smaller amount of data, which is to say bigger than would make sense for a really huge fleet of M1 extra larges, but they have really dense query workloads. So they're always wanting to keep that active data not just available in solid state storage, but even wanting to keep it in memory. So the 15 gigabytes of RAM available in the M1 extra large instances is awful nice. But those CR1 8XL instances have 244 gigs of RAM. So a much, much bigger footprint to store terabyte class data sets in Cassandra in memory, which allows radically faster access to query performance, higher numbers of concurrent queries, and generally is a higher density solution. So lots of different paths there.
Thank you, Miles. We have very engaged audience today. We might not be able to cover all questions, but we will do our best. And for those questions that we cannot provide answers today, you will receive answers during the week directly from Stackdriver. Joey, my next question is to you. How do I make sure my distributed Cassandra cluster is running properly?
Okay, great question. So that's actually one thing that I didn't get into is basically this is how do you monitor your Cassandra cluster. So one of the problems with monitoring the Cassandra cluster is that you have a constant you may have a constant stream of changing nodes, right? So nodes are added and removed as you need to. So you need a way to make sure that when nodes are added, they're kind of automatically added to your monitoring. That's one thing that you need to solve. Specifically on metrics that we look at, we use a tool here at Stackdriver called JMX Trans. That's an open source tool, and it collects JMX metrics and writes them to optionally graphite. We've written a backend here for Stackdriver, so you can write them to Stackdriver. And I believe it supports Ganglia and RRD tool as well, a couple other open source tools. So JMX Trans will ship us data about internal metrics about how Cassandra is performing. So some key metrics I'll just kind of list off. One is storage load. This is how much data is on each one of your nodes. This tells you, how dense each one of your nodes is. So if you have, let's say, 600 gigs of data on each node, that starts to be a lot of data. Another metric that we monitor is pending compactions. The higher this number is, the further behind your Cassandra cluster is in compacting new data. So I briefly touched on this earlier, but when data is written to the commit log first, and then when enough data come in, it's compacted and put into SS tables. And so this is the number of jobs that are waiting for compaction. And then we actually, using JMX Trans still, we'll keep an eye on thread count and open file descriptors. And what you want to look for there is any of these metrics that kind of are on a runaway. So obviously there's a ceiling for how many threads or open file descriptors that you can have. And you want to monitor based on what your boundaries are. And then yep.
I thought you were done. I'm sorry.
No, it's all right. Just one other metric that we're also keeping an eye on, and this is specific to the JVM, is just how much garbage collection is going on. And what we found is some nodes will get into a weird state and have higher garbage collection than others. And we know that those are operating outside the normal bounds, and we'll go ahead and replace those.
Thank you. A few more questions to you, Joey. And how do you handle the deployment of any DB changes in production?
Yeah, so I think you're specifically talking about schema changes. So Cassandra supports online schema changes. So our process is that we'll test the schema changes in a staging environment, make sure that all the readers and writers are compatible, and then we'll push this out to production. So usually a schema change is pretty rare for us, and it tends to be a manual operation.
Thanks. And do you use caching for read operations?
Today we don't. Yeah, today we don't.
Let's take one more question, and I'm going to point this to Miles. Why are you using ephemeral disk but not EBS?
Sure. So we have huge numbers of customers, frankly, that are using Cassandra with EBS. It's a popular implementation as well. There are different sizes of EC2 instances that offer different amounts, different ratios of compute to memory to network performance to storage. The advantage for Cassandra for access to local disk is that it is very much a storage-bound workload in most cases. On AWS, when you communicate with EBS, you do that over the network connection. And so we have EC2 instances, say like an M1 small or an M1 medium or even, C1 medium, these smaller size instances. Those share a network connection between the network that gets used for internet or machine-to-machine communications with the network that communicates to EBS. So there's a limited amount of bandwidth between storage and the instance that contends with the bandwidth that you're using to replicate data between nodes, between EC2 instances in the Cassandra fleet. So by using local disk, you reduce the amount of network traffic used because you're only now using network traffic to manage replication between the cluster nodes rather than also using it to communicate with EBS. Now, EBS has added a feature together with EC2 called EBS Optimize that adds, for some instances, 500 megabits per second for the larger instances like the M1 extra large, a gigabit per second of network throughput to EBS that's dedicated, isolated from the standard network connectivity. So we would strongly recommend, if you're going to run Cassandra and use EBS storage, which might make a lot of sense if you have really, really big data sets that you operate a relatively small number of queries for. So you could have instances with 20, 30 terabytes of EBS storage attached, connected over networks on these smaller instance sizes. Those kinds of designs and those kinds of workload patterns would take big advantage of the lower instance cost in comparison to a slightly elevated storage cost associated with attaching EBS. So it really has to do with lining up with your specific use case and ensuring that that you have the right ratio of storage and compute performance to the network resource that you have.
Thank you, Miles. We'll have to end our Q&A right now, but all the questions will be answered via email or other form of communication through Stackdriver. And I'd like to thank everybody for attending this webinar, and our speakers. Thank you for demonstrating the best practices for running Apache Cassandra on AWS. And our attendees, before you log off, we appreciate your answers to a short survey. It's very short, but it will help us improve our webinar series. So just click the link that will appear on your browser, and it will take you right to the survey site. Once again, thank you very much for attending, and this concludes today's Amazon Web Services Partner Webcast. Have a great day.